So the idea of my talk today is to show how we are dating shear zones nowadays and what's my perspective on what we should be doing from today to the future. So I just want to give a few simple definitions about shear zones and mylonites, which are typical rocks of shear zones. So shear zones, in the most simple definitions, are just high strain zones that accommodate lateral displacement of adjoint volumes of rocks. So this is one of the shear zones I visited during my bachelor's degree in Brazil. So it's a massive shear zone, high-grade shear zone, granulite facies, and you can really see it's extremely deformed, really high intense strain concentration. And the rocks that we have in these shear zones are what we call mylonites. So there are several definitions for mylonites, protomylonites, ultramylonites, but the most simple definition we can use is that mylonites are rocks with a strong foliation and lineation fabric that develop fine-grained recrystallized matrix and generally porphyroclast. So here we have this is from the same shear zone that we were seeing before. So a massive amphibolite bulldon with this melanitic foliation, passive folds, here a feldspar porphyroclast and another bulldon in the melanitic foliation. So these definitions will be very important for what I'm proposing that we should be doing in the next, to improve our knowledge in the geochronology of shear zones. This is another nice SC fabric mylonite from another shear zone in Brazil, and this is from the Atlas of Mylonite book. So one thing that I think is really important for us to understand about geochronology of shear zones is that mylonites are rocks that are recrystallized. So when we think about recrystallization, which is, again, the simple definition is the reorganization of material with a change in grain size, shape, and orientation within the same mineral, for example, quartz, which is very common in mylonites. And the most important factors for recrystallization is temperature, strain rate, stress flow, and fluids. And this is all to reduce the internal free energy, looking for the mineral most stable situation. So how can we date shear zones? We can date in two ways, pretty much. The first way is an indirect way. So I just picked up one of the papers that I know that use this indirect framework to date the shear zone. So they dated a deformed gabbro with zircon granulate, and they said that, look, we have this deformed gabbro that was crystallized at 610 million years, but then undeformed leucogranite monazite granulate, it's 550, and it's cross-cutting the shear zone. So the minimum that we can infer here is that at 610, the shear zone was being active, deforming and recrystallizing rocks. And at 510, you already stopped in the place that they were studying because the rock that is cross-cutting the shear zone is not even deformed anymore. So this is a very indirect way. It gives us like a 60 million years deformation interval. And within these 60 million years, a lot can happen. So this is a very just indirect way to date a shear zone. We can also do a more direct way, especially if you're looking at high-grade shear zones that goes to upper amphibolite to granulite facies where zircon, monazite, and titanite are prone to recrystallize and record the age of deformation. Or when you're looking at low-grade shear zones below lower amphibolite facies or lower green schist facies, you can use potassium argon and argon in micas, biotite, and muscovite, which is the closure temperature is more related to the deformation temperatures. So that's okay. But what happened to the medium-grade shear zones? So zircon doesn't recrystallize in medium-grade shear zones. Monazites and titanites generally higher grade, and the micas in potassium argon and argon should be lower temperature already. So some things we can do is rubidium-strontium in muscovite, argon in hornblende, but the argon in hornblende is a little bit of a problem because hornblende is more towards mafic rocks, so you don't have a lot of hornblende felsic rocks. And of course, uranilating and apatite. So I'm going to show one of my studies that I did with apatite. I was studying a shear zone in Brazil, and my idea was to understand if the apatite can actually be reset by deformation. So just to give a brief idea, this shear zone was deforming some granites, they are 600 million years, and they form a very large variety of mylonites. So you have these SC fabric mylonites with nice fish micas, a lot of very complicated textures of mica deformation, and here you have the apatite. So all the apatites, they have a very euhedral geometry, so they look like a igneous apatite. So the idea was to understand if these apatites were thermally reset by deformation or not. The approach that I took from this work was to date apatite from the granites and also apatites from the mylonites, which are granitic mylonites. And I'm also using argon-argon to compare with the apatite ages. The good thing of the shear zone is that in a previous paper that I published before, we determined the conditions of deformation, that it ranges from 480 degrees Celsius to 530 degrees Celsius with different methods. So we had a very nice thermal constraint to compare all the closure temperatures that we get from different minerals to the deformation condition. So remember that I said that the granite is about 600 million years, and the apatite that we got from the granites are very concordant with the zircon uranilite ages. So from one sample we got 611 plus minus 6, the other one is 593 plus minus 10. When we move to the granite, to the granitic mylonites, I also dated zircons and titanites, which were supposed to date the protolith because they are not able to, theoretically not able to reset. And then we actually got older ages, like the granitic crystallization age, which is 606 plus minus 4 in the zircon and 604 plus minus 8 in the titanite. But when we move to the apatite, we actually get much younger ages at 544 plus minus 3, 547 plus minus 11. So this is already indicating to us that the apatite has been thermally reset, or at least reset. When we see the argon-argon, we have so these two samples were, this sample were analyzed in Brazil. These two samples were analyzed here in Australia. The problem that we have in analyzing different labs is that we have different analytical precision. So these instruments are much more precise, so we don't have plateau. So if these boxes were larger, we would probably have like an apparent plateau, but this is just a analytical precision problem. So this is the most reliable sample that we have at 536 plus minus 3 million years. This is 500 plus 42 plus minus 2, but if there was a smaller, the precision was better, we would probably have this saddle shape spectrum like we have in these samples. So we observed that it's really common that the deformed micas, you have all the 39 argon excess recoil, and then you get this saddle shape spectrum, which leads to a overestimation in the age. So it's not a very good method for my study case. So someone could just say that the apatites are metamorphic, and they were recrystallizing during deformation. But the trace elements that we have, they are all similar to the igneous apatites from the granites, and the disturbance that we observe here is probably related to a igneous moment hydro alteration than the proper metamorphic process changing the chemistry of the apatite. So we assume that we interpret this as the apatites as being primarily igneous and just being thermally reset by the buffer temperature of the deformation. And the same thing happens to the titanite. So the titanite, we did some modeling with the zirconium in titanite thermometer, and all the temperatures that we got here, so it's pretty much around 700 degrees, which is much higher than the deformation temperature of the shear zone, which is why the titanite still retains the igneous age. So the conclusions of my paper is that apatite is actually able to reset the UPB system at conditions between 420 to 500 degrees, which gives us a time estimate for the shear zone between 560 to 535 million years when we couple this to the argon-argon results that we have. So okay, the conclusions that we get from this is that apatite is actually a very good geochronometer for medium grade shear zones. And I'm not the first person to say this anyway. But what about the fabric and the strain evolution of myelonites? Because that's what makes a myelonite, right? So there's the strain and the temperature that is being applied to the rock that enhances crystallization and recrystallization of the rock. How can we actually demonstrate that the agent that we're getting here is actually related to certain processes of deformation instead of just a thermal buffer from deformation? So I brought a few examples, and these are all my examples, very selfish rocks. So this is from my JMG paper recently published last year. I would say that I dated apatite from these samples and micas, and this from the microstructures, I would infer that the deformation play a role at between 450 to 500 degrees. Would you think that the apatite and the mica age would be the same or different? They are the same. So the apatite age is from this rock. So this is a 2 billion years rock in zircon-uranium lead. The apatite is 1.77 billion years, 1769 plus minus 38 million years. And the rubidium and micas, all in situ, dated 1778 plus minus 11. So this other rock is from the same place, so it's actually the same complex. It's also 2 billion years, but the deformation is a little bit lower degree at 400 to 450 degrees. I also have apatite and micas, but the ages are different. We have this 1970 plus minus 47 million years, which is the crystallization age of the rock, the igneous crystallization. But the fabric is actually 1629 plus minus 23. When we look at this, this is a SC P-Light. So you have very nice SC fabrics. This is all biotite and a little bit of this is all muscovite with just a little bit of biotite and garnet, very small garnet. Maybe this will be better. So you have these biotite grains here, very fine grains. All these SC fabrics of micas and these very tiny grains of garnet that sometimes it shows to be prekinematics. Sometimes it shows to be synkinematics. It's a bit uncertain. So I did lutetium hafnium garnet in situ and also rubidium in situ in the micas. And we get very different ages. Well, not very different, but significantly different. In the garnet, we get 1348 plus minus 24 million years. It's a very complex garnet. There's a lot of processes happening here, but the ages are pretty much coming from the core of the garnets. And the micas that we have here are not actually muscovite, they are fangites. So it's a very unexpected rock to be high pressure rock. And the age that we get is 1264 plus minus 18 million years. So if you just get one single mineral from this rock, you're probably losing a lot of information and tectonic processes that the rock was being recorded in different systems and different minerals. And why we are being able to do this is because of the new mass spectrometers that we have nowadays. We can do in situ rubidium in micas, for example, muscovite, or in situ lutetium hafnium garnet. And this wasn't possible before because of the isobaric interferences. I'm just go through this very quickly. For example, rubidium-87 and strontium-87, they all look the same for the mass spectrometer because it measures mass and charge, right? So they will all look the same, similar as to 176, lutetium, ytterbium, and hafnium. They all look the same for the mass spectrometer. But when you have some mass spectrometers that you have collision cells inside, you can put some oxidizing gas, create a mass shift, and then you can measure, for example, 87 strontium plus 16, and then rubidium goes free. So you can actually separate the isotopes by a collision cell system. So we can do this using a triple quadrupole, which is exactly what we have here. So this is the collision cell where you put the gas, and then you create the complexes that you want to analyze separately to isolate the interference. And nowadays we also have a new multi-collector called NEOMA that increases the resolution, higher sensitivity, and then we can go in smaller spot size. This will enhance the in situ and textural control avenue that we can do for deformed rocks and very fine grain minerals that it's in the fabric. So this is the whole point of our talk today, this rock. So this rock is from West Arunta, and it's a mylonite. It's a medium grade mylonite. I want to say a few things about the textures. So you have here pretty much a quartz dominated band or layer, and then in this band layer you have these coarse grained micas, but in here in this domain it's much more feldspar dominated. So when you think about a rock being deformed, deformation is not the same every place in the rock. It gets localized, temperature is different, and minerals behave differently in different parts of the rock. So this is a TEMA map, just a automatic mineral identification, just highlighting the muscovite with the background. And just to give a brief overview of the mineralogy, we have pretty much 30% quartz, 31% plagioclase, 20% alkali feldspar, 13% muscovite, 6% minors. And this rock, when you think, let's get the crystallization age of this rock, but we have literally 0% zircon, no monazite, no titanite, and 0.06% of apatite. And they are very tiny. So these are these yellow dots here. So what do you do with this rock? You date the micas. And then when you go for the micas, oh well, the microstructures again, just highlighting the different. So this is the fish-shaped micas in the quartz deformed, in the quartz band, and this is just shear bands in the rock that is here. So you can see that they have very, very different microstructures. They look very different, but they are the same mica. So this frame is going to be very important for us. And all of these holes here are laser pits. When you go for dating these rocks, I dated the shear bands and also the big grains. And then imagine that I only have this. And my initial thought was something went wrong with the analytical session. There was a drift and all the data was wrong at some point. But then I actually realized that we have different microstructures and different mechanisms of deformation. So these micas are actually being intracrystalline deformed. So they are creating slips inside the system. They are being folded. You see that there's a lot of undulose and extinction in these rocks in the micas that demonstrated that the intracrystalline system is being slipped. Whereas this one, you see a very big grain size reduction. So the grain size is much smaller. There's no undulose extinction, for example. They are pretty much randomly oriented, for example, here, and they're much finer. So from these grains, the bigger grains, we get a aerochrome age. So it's not a statistically reliable age of 1653 plus minus 36 million years. But then using the initial ratio and the older and younger grains, we can define that the ages or the data is being spread out between 1.7 and 1.58 billion years. When we look at the finer grains here, we get a very young age at 594 plus minus 26 million years, or 583 plus minus 6 when you anchor to the plagioclase. So they are pretty much the same. So if we didn't look at the microstructures and how the deformation is being localized, the strain is being localized in the rock because of the mineralogy that the mica is around, we would lose a billion years deformation story. So that's pretty significant, I guess. This is just to demonstrate that along the mica in parallel to the elongation and perpendicular to the elongation, the isotopic ratios are all the same, which is not suggesting that this spread that we have here is just an intracrystalline problem. And the problem with this with this sample is that we didn't have anything to compare with the age. So is this what the older age means? Because the younger one, it's really clear that it's a strain that it's being localized in the margins of the porphyroclasts and just leading the micas to be recrystallized and grain size reducted. So we dated garnets again with lutetium hafnium in situ so this sample is from the same drill core as this one, and we get 1696 plus minus 43, which matches pretty well with these ages. And this is 50 kilometers away from this drill core, which is again 1670 plus minus 36 million years. So now we can tie that this deformational process is a metamorphic event that play around 1670 to 1.7 billion years, which agrees pretty well with the array of ages that we get from the coarse grain deformed micas. And this age, it wouldn't be possible to pick without dating the fabric, which is dating the strain and deformation in the end. This is a electron backscattering diffraction map. So what this map shows is how the micas are being oriented, crystallographic oriented. This map is just a grain size map. So we can see, for example, here in the pressure shadow, all the micas being a little bit more coarse. But when you come to this high, pretty much like a pinch structure, where you have this feldspar porphyroclast, this feldspar porphyroclast and quartz, the strain gets so intense that all the grains go really, really small because the strain is very high. This is what we call segmentation or grain size reduction. This is just a histogram with the number of grains versus this is wrong, it's just the grain size. So it's a asymmetrical positive distribution with large dominance of small grains because of recrystallization. This is just a textural component map. So this big grain, you can see different shades of brown. And this is showing us that subgrains are actually being created inside the big grain. We can see this through the cumulative misorientation profile. So we can see these steps. It's really typical of grains that are being recrystallized and creating subgrain rotation due to intracrystalline deformation. And when you see the other grains here, like for example these ones, they don't have these tones of, different tones of brown because they have a lower internal energy. They are much more stable. They were crystallized, not recrystallized. They were just created or segmented during deformation due to high strain. So they are already very stable. So how should we date mylonites in general? We can do book grain geochronology. Sure, we can do UPB for zircon monazite and titanite for high grade. Sure, that works. Medium grade, we can use uranylating and apatite, or even recrystallized monazite and titanite. That will also work. And low grade, we can do potassium argon and argon-argon in micas. That all work. But this is giving us the thermal constraint of deformation, not the proper strain partitioning in the rock and how strain is affecting the rock and the geochronometers. So just going back again for what is a myeloid. Myeloid is a fine grain recrystallizing matrix with porphyroclasts. And the key factors again is temperature, strain, and fluids. But here I want to focus on strain because strain gets partitioned in the rock depending on the mineralogy that you have. So if you have a quartz band and a layer with more porphyroclasts, strain is going to be partitioned and minerals will deform differently. And this enhances localization. So strain gets localized in the, for example, porphyroclast margins, and everything that it's around the porphyroclast margins will be more prone to face the low temperature strain, high strain events than the domains that are quartz dominated, because quartz more prone to absorb the strain than the other phases. So my final considerations for this talk is that, it's okay, no, it's fine. That bulk grain geochronology gives us time temperature constraints for shear zones. And sometimes that this is everything we want, right? That it's okay. And the problem with this is that it needs to be associated with pressure temperature quantifications to say, look, my shear zone was deformed, I don't know, 600 degrees. My mineral has a closure temperature between 450 to 650, whatever. So it's possible that the age that we're getting is much younger than the crystallization age. It might be related to the thermal buffer related to deformation. Sure, that's fine. But when we go for in situ textural geochronology, you have a much higher resolution in regards to deformation and time relationship. You can say that at a certain time, so in my rock, for example, at 590, there was a cryptic reactivation event at lower temperature that wasn't able to thermally reset the other minerals or the other mica microstructures, for example. And this is also very important for the mechanisms of deformation, how different grains are being deformed in different rocks or in different domains of the rocks because of how the mineralogy is being distributed in the rock and how strain is being partitioned and localized in the rock. And again, this is really important for low temperature reactivations in intracontinental settings, for example, where the thermal buffer is probably not high enough to reset the chronometer of different minerals. And then you really have to look at the different mechanisms of deformation and when the mechanisms actually change and how the microstructure related to the age that you're getting. And this is really important when you start looking to the fabric and how the fabric has changed to link with different PT conditions. So for example, we can do an electron microprobe map here and see the distribution of elements in the mica to put in the thermodynamic modeling, or just titanium thermometer in mica to calculate the temperature. We might be actually lower, or just fluid decompositions, because fluid drives recrystallization. So if you have micas like this and you have evidence that this is being enhanced by fluid, you can actually analyze these micas with oxygen isotopes, and then you can relate the age that we're getting from this fine grain micas with oxygen isotopes, and then you can link fluid flow and deformation and ages at a certain time that you wouldn't be able to do if you didn't look at the fabric. So with this, think that we have to change the perspective of how we date myelonites. I'm done, and I hope you like it, and I'm open for questions.